Welcome back to the podcast. Today, we're diving into the intriguing world of data querying languages, specifically looking at the differences between declarative and imperative approaches. If you've ever wondered why some languages are favored for styling documents or querying databases, you're in for a treat. We'll explore examples from CSS, XSL, JavaScript, SQL, and even venture into the realm of graph databases. So grab your headphones and let's get started. Let's kick things off by examining declarative languages like CSS and XSL. These languages allow you to specify what you want to achieve without detailing how to do it. For instance, in CSS, setting the background color of a selected list item is as simple as writing a rule like li.selected-p background color blue. In XSL, a similar approach is employed. The code applies a blue background to paragraphs within selected list items, showcasing the elegance and straightforwardness of declarative syntax. Now let's contrast that with an imperative approach using JavaScript. This is where things can get a bit messy. To achieve the same effect of highlighting a selected item, you'd need to write a lengthy script that iterates through list items, checks their classes, and applies styles accordingly. This imperative code not only tends to be longer, but also becomes harder to read and maintain. For example, if a user clicks away and the selected class is removed, the blue background remains until the page is reloaded. This is a significant drawback compared to CSS, where the browser automatically updates styles based on class changes. Just like we see in styling languages, similar principles apply to databases. Declarative query languages like SQL have proven to be far superior to imperative query APIs. Instead of writing code to manipulate data, record by record, SQL lets you express what data you want in a much more concise way. For example, if you want to generate a report of shark sightings per month, a simple SQL query can group and sum the data efficiently. The beauty of SQL lies in its ability to optimize queries behind the scenes, something that imperative languages often struggle with. Now, let's touch on MapReduce, a model popularized by Google for processing large data sets across distributed systems. MapReduce serves as a middle ground between the two approaches. It uses a functional programming style where you define map and reduce functions for processing data. In MongoDB, for instance, you might write a map function to emit key value pairs based on shark sightings, and a reduce function to sum those values. While powerful, this method requires careful coordination between the two functions, which can be more complex than a single declarative query. To simplify things, MongoDB introduced the aggregation pipeline, which allows for a more declarative approach to querying. This enables you to easily filter and group data using a JSON-like syntax. So, if you want to count sharks, you can match the family and group by year and month in a single, readable command. This shift highlights a trend in NoSQL databases. They often reinvent SQL-like functionality, albeit in different formats, to provide users with the flexibility and power they need. As we explore data modeling, it's crucial to understand the relationships between data. Many applications have one-to-many relationships, which fit well into document models. However, when it comes to many-to-many relationships, graph databases truly shine. Graphs consist of vertices, or nodes, and edges, which represent relationships, making them ideal for complex connections. For example, in social networks, vertices can represent users, while edges represent friendships. This structure allows for powerful algorithms to operate on the data, like finding the shortest path in navigation systems. In the realm of graph databases, we have several declarative query languages such as Cypher for Neo4j and Sparkle for RDF data. These languages allow users to express complex queries about relationships in a straightforward manner. In a property graph model, for instance, each vertex can have multiple edges and properties, enabling rich data representation. The flexibility of graph databases means you can model various data types and relationships without being constrained by a rigid schema. When working with graphs, each vertex can have a unique identifier and properties, while edges define the relationships between them. This structure not only facilitates efficient queries, but also allows for a clean data model that can evolve over time. For example, in a social network graph, you might have vertices representing people, events, and locations, with edges indicating friendships, attendance, and interactions. This interconnectedness is what makes graph databases so powerful for applications that require complex data relationships. In summary, we've explored the differences between declarative and imperative languages in the context of data querying and modeling. We've seen how declarative languages like CSS and SQL provide clarity and efficiency, while imperative languages can lead to complexity and maintenance challenges. From traditional SQL to the innovative aggregation pipelines in MongoDB and the powerful capabilities of graph databases, it's clear that understanding these concepts is crucial for anyone working with data. As technology continues to evolve, the trend towards declarative approaches is growing, offering us more intuitive and powerful ways to interact with our data. Thanks for tuning in today. We hope you found this discussion enlightening. Don't forget to subscribe and join us next time as we delve deeper into the world of data and technology. Until then, keep exploring.